This is the solution for the second problem, or problem 12 on the exam, and we are asked to find the coefficient of friction that prevents the ladder from slipping. If you recall, the coefficient of friction is given by the friction force divided by the normal force. On the right hand side, I have drawn the free body diagram. We have the normal force from the ground on the ladder. We have the friction force on the ladder. We have the mass of the ladder times G, which is the weight of the ladder located in the middle of the ladder, since the ladder is symmetric. And then we have a force on the ladder from Romeo, who's 90% above the length of the ladder. And then finally we have a force from the wall normal to the ladder. Let's pick this point here as O, our pivot point, because we will need to use some equilibrium conditions. And if you remember that the sum of the torques around a pivot point under equilibrium has to be 0, that will allow us to get rid of or cancel out the contributions of the normal force and the friction force on this pivot point. And the first one we see is the halfway up the ladder, so that's 0.5 L cosine theta that times the mass of the ladder times G. And then we have another counterclockwise torque from Romeo, which is 0.9 of the length of the ladder times mass of Romeo times G. And then the force from the wall applies a torque that has a distance L sine theta times FW equals 0. And if you note, theta has a cosine inverse of 2.8 meters divided by 10 meters, which gives us an angle of about 73.74 degrees. And if I look at the force on the wall and solve for it, I will get that FW equals 0.9 mass of Romeo. Notice that every term that I'm going to write in this bracket has a G in it and a cosine theta, so I'm going to factor those out. Then I have 0.5 mass of ladder. Then I have G cosine theta. Notice also that every term has an L, and those can cancel out. And then if I divide by what's next to FW, which is the sine theta, I now have an expression for the force on the wall. So now we can plug in our values. 0.9 times, we know that mass of Romeo is 70 kilograms. We are given that the mass of the ladder is 22 kilograms times G, which is 9.8 meters per second squared, times the cosine of 73.74 degrees. Make sure when you plug this in your calculator you're in degree modes, times divided by the sine of the angle theta, or sine of 73.74. And this will give us a value for FW that is 211.7 newtons. So we're on our way to finding the solution, and now we can say, well, since it's in equilibrium, the sum of the forces in the x direction have to be 0, and if I scroll back up, I notice that I only have two forces that are acting in the x direction, which are F sub W in the negative and the friction in the positive. So this means that the friction force is the same as Fw, which we just found up in the previous calculation of 211.7. So we have our first piece to find the coefficient of friction, and the last condition we have is that the sum of the forces in the y direction has to be 0. Again, if you look at the equation, the free body diagram, you notice that we have some forces in the y, and if we use our convention, we have normal force to the top, the mass of Romeo times g pointing downward, the mass of the ladder times g pointing downward. Those are the only forces in the y direction. Set that equal to 0, and you find out that F sub n then is, I'm going to factor out the g, so I get m sub r plus m sub l all times g. And if I plug in these numbers, I get 70 kilograms plus 22 kilograms times 9.8 meters per second squared, which gives me a normal force of, 902.5 newtons. And now we can say that the coefficient of friction, which is the friction force divided by the normal force, is going to be 211.7 newtons divided by 902.5 newtons, or 0.23.